Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, good afternoon, everybody. Let's get started. My name is Ratul Mahajan. I work here at Microsoft Research, and with great pleasure, along with Nikolai, who's also my colleague at Microsoft Research, welcome you to the network verification session. Actually, to be fair, I think Nikolai and I are just puppets. This session's the brainchild of George. Here you'll hear second, and he's like the real puppet master here. But getting to the topic of this session is basically network verification, and the motivation is simple for anybody who runs networks that are more than 2 routers would know how messy today's networks are, and not to even talk about how complex networks at large companies like ours at Microsoft are, to the extent that even it's hard to reason about even something that's made up of like 3 routers, I would say. And I think there's a theme of research that has been going on for the last few years trying to essentially make sense of it. The focus of this session is essentially to say what inspiration we can draw from the fields of hardware and software verification to make our networks more understandable, correct, and verifiable. And we have essentially we have an excellent line of speakers who've done a lot of work in this particular area, and this is what each of the speakers is going to focus on. We'll start with Sharad, who is well known in the field of EDA and design automation and analysis, and we'll move on to George, Jeff, and Nate, and we'll introduce the speakers as they kind of go along. The whole purpose would be to essentially draw parallels and see what we can learn from EDA as applied to network design automation. And the merger here is somewhat natural for those of you who have not followed design automation, is that a lot of the design automation tools have verification at the heart of them. So in the sense, you can think about verification being a precursor to design automation as well. So we'll kind of follow that journey along with these speakers who've seen this happen in some way or the other. So then without much ado, I'd like to welcome Sharad as the first speaker. For those of you who don't know Sharad, he's actually very famous in this community. But he received his bachelor's degree at Indian Institute of Technology, Delhi. I kind of proudly say that. I went to the same college. And right now, he's a professor at Princeton University, and Sharad's done some foundational work on propositional satisfiability that's being used in a lot of industrial design automation tools. And he's won a bunch of awards for his papers, like especially 50-year most cited papers or 10-year retrospectives. Those are the kinds of awards that the computer science community really values, and Sharad has not just one, but many others. And today he's going to talk about what lessons we, the networking community, learn from what he's seen from EDA.
Yeah. Welcome.
Thank you. Can you just get my slide up? Okay, while this is going up, thanks a lot for this introduction, this invitation. It's really a pleasure being here and getting to learn from a very diverse community here. So as Ratul pointed out, my background is in electronic design automation, and I have very little background in networking. So what I'll be talking about is my perspectives from my background in electronic design automation coming into network verification. And I'll talk a little bit about the work that I've done there, but mostly what I'll be talking about is lessons learned, at least in terms of how the whole field has evolved in terms of electronic design automation, and what lessons there might be for possibly network design automation if that were to exist as an entity of its own. So if you look at electronic, okay, so it's a little slow. So if you look at electronic design automation, this is a very well-established industry. It's a $4 billion annual revenue industry, which then feeds into a $350 billion semiconductor industry, which then feeds into a $3 trillion electronics industry. So essentially, everything at the heart of this is enabled by chips that then get designed by these tools. And but if you look at these tools really, it's not just these tools that are at the heart of EDA, but really, it's a whole design methodology that these tools are part of. And that's one of the key messages that I want to make sure that goes through. That is, there's a very keen interplay between design automation and design methodology, and we shouldn't be looking at one without the other. So in particular, I'll start off with a few components of this. Okay, so this is a little slow. I'm just going to go to the podium here. It'll be faster. So then I can't see the screen, so I have to come back. So one of the key components of this interplay is that these design tools impose a certain discipline in the design methodology. And in particular, what I mean by this discipline is that you have a disciplined restriction of possible choices. So when we do design, we really have a whole palette in front of us in terms of the things we can do. What design discipline does for us is it forces us to make certain restrictions in what we are allowed to do, what we are not allowed to do. And this happens in multiple areas, not just electronic design. And I'll give a sort of classic example of this. Actually, would it be possible to switch this? This is not, I can get one. Okay. Yeah. I'm not sure where it plugs in, though. Oh, I suspect it's got to do more with the fact that this is boxed up rather than the pointer itself. Okay. So I guess it's a distance issue, so I need to be closer here. Okay, so let me give a sort of classic example of design discipline. And so if you look at digital design, it's almost universally done using what's called a synchronous design methodology. And what that means is that we restrict ourselves to a style of design where all the state changes, all the memory elements that are storing state, they all change synchronously with respect to the clock. Today we take it for granted, but we don't have to do it this way. This is not the only way we can do design. But what this does for us is it ensures that all state changes at the same time. So the state at time t plus 1 is some function, this function f, which is computed by this piece of combinational logic of the state at time t and the external inputs. So if you're thinking about network design methodology and network design automation, I think then we have to look at, so what are the elements of design discipline that would go into this that would help that process? So I'm going to be asking a lot of questions and not providing too many answers, largely because I don't know the answers. I'm hoping that they'll come out of conversations that result at the end of this. So the second element that we have that shows this interplay between design automation and design methodology is that any design process goes through a flow of design refinement. So in the hardware case, what you have is you start off with a design that's referred to as a behavioral design. And really at this level, all you're doing is you're describing functions that modify state, update state. This then goes through some synthesis, which converts it into a logic design, which is gates and the interconnections, which then goes to some further steps into some physical and mass design, which really then at that point is referring to objects which have coordinates, 2D and 3D coordinates. And so what's going on during this process is there's a whole bunch of design tools that are helping you go through these steps. And these tools match the level of abstraction. So each of these tools works on a given level of abstraction, understands that pretty well. And that's where all the algorithms are built in, all the analysis techniques are built in. So again, the corresponding question is that, if you're going to look at network design, what are the design flows and abstractions? And people have to sort of agree on these. These have to be agreed on by the community. And so is it a more ad hoc process? Or is it a more structured process that looks like this? Because this is really what we'll need it to look like if we hope to do any serious automation there. So the third component that I'm going to talk about here is this design process, which is referred to as design by composition. And this is something that we do in software all the time, and we're doing it in hardware. That's the only way we can build large, complex systems. And really what this means is that with standardized interfaces such as cell libraries, memory interfaces, bus interfaces, we can compose large designs by just plugging in different alternatives for smaller components. Okay, so it's a fairly standard concept. We understand this. While it may seem trivial, but we absolutely, for a systematic design methodology with automation, we will need standardized interfaces for design by composition. And the question is, what are these for network design today? So as we look at this interplay between design methodology and design tools, so the first thing that I immediately I realized was that in hardware design, we really didn't have a choice in terms of design automation. So here's the obligatory Moore's law slide. The complexity pretty much forced us to have automation. There's no way we could have had the design process go without automation here. And in fact, in this area, we have had this wonderful bootstrapping arrangement where we've used today's computers to design tomorrow's computers. But this complexity is not limited to processor chips. If we just look at the whole range of digital electronics that we design, even non-processor designs have very significant complexity of the order of hundreds of millions of gates. Now, if I take this particular analogy and apply it to network design, I really don't think that the growing network complexity is going to be the driver for network design automation. And the reason for that is we already have large complex networks, and we don't have network design automation. So we've done pretty well in terms of network design, at least in terms of making these products, selling them, and so on. So this I don't believe is going to be the driver. This complexity is not going to be the driver. In that sense, this is more like the software industry, where, again, software is complex. But in terms of automation and methodology, there's really not something that's very standard that people all systematically follow. But if we then narrow down automation to just the verification part, and again, in the hardware case, this became very necessary. And it's necessary because of the high cost of failure. So in particular, the thing that really demands this is the need for first silicon success. That is, the first chip that gets fabricated out has to work. Or there's a high economic incentive to make it work. It doesn't always work, but there's a high economic incentive to make it work. So we essentially have to have working parts right off the fabrication line. And the reason for that is the mask costs are very high. So if the part doesn't work, you have to go back and redo the masks. You're going to pay in excess of tens of millions of dollars to do a fresh set of masks. But more important is the cost of product recall. So for those of you who are old enough to remember this, so in 1994, there was a famous Intel Pentium FDiv bug. And these are the two arguments that resulted in an incorrect result in floating point division. And this was very expensive. Intel had to do a product recall. Cost was roughly $500 million. Now, this one incident I credit as being the single largest reason why we have formal verification today in both the hardware and the software communities. Because this cost essentially prompted a big push in the industry to have formal techniques where you could have proofs of correctness in advance of designs being ready and shipped. So if I look at the corresponding questions and say, OK, so in network verification, this I believe is already true. That is, the downtime costs and security breach costs are, I think, very compelling for network verification. So I don't even list this as a question. I just list this as a statement. I believe that this is a significant driver, sufficient driver for automation in network verification. But if you look at a broader network design automation, let's go back to EDA and see that in addition to it being necessary, it actually has been very valuable. It's provided many significant things that have made it a key part of what we do today. So of course, it's given us design scalability, the ability to handle larger designs. It, in addition, has given us design diversity. Because we can automate and have a methodology that lets us design in a fairly systematic way, we can build a big range of components. We're not just building processors. We are building all kinds of different chips in different products. And the reason for this is that we can very quickly put together specialized functional units. These are referred to as intellectual property in the semiconductor business. And then we can take these and assemble these in systems on a chip, where if we look at designs today, a chip on the average has more than 80 of these intellectual property blocks. So these could be, for example, a video compressor, decompressor, encryption block, and so on. And each of these actually is really a whole subsystem. So each of them, in turn, is composed of many more blocks. And equally important is the role that EDA plays in design optimization, that is, in reducing part costs, which in turn help enable new functionality, because things that you wouldn't have been able to afford or build otherwise in either dollar cost, or they weren't fast enough, they weren't good enough to do what you wanted to do, or they consume too much power. So optimization sort of pushes this envelope, pushes this frontier such that you can now push this to include new functionality, new parts that provide new value that you wouldn't have been able to do otherwise. And it is this part that I think really will be the compelling advantage for network design automation. That is, even though we don't need it from a pure complexity point of view, but the benefits from scalability, the diversity of different parts, parts in this case, different kinds of networks that you could build, and then novel functionality, I think there's enough compelling advantage here that if you're looking at network design automation, this could provide that. There's also some value in looking at how EDA has evolved over time. So it started off as just being models. So for example, things like SPICE models, which were nothing but equations that model semiconductor devices. Then this very quickly, as we got to more complex designs, got replaced by even not replaced, but supplemented by specification mechanisms like Verilog, which is a hardware design language. But if you look at these languages, they're not only specification languages, but they have an underlying model, which obviously you need to understand what is it that these designs are actually doing. The models were followed very quickly with analysis. And by analysis, I mean things like timing analysis, where you can determine for a given circuit how fast you can clock it, functional analysis, what exactly does it do, and this really is the heart of functional verification. Once you have models and analysis, the analysis you can use in an inner loop for optimization, and that's what happened. And then finally, once you have the ability to optimize, you can go all the way from specification to optimize designs from these specifications, which is referred to as synthesis. The key point I want to make here is that these two parts, modeling and analysis, is really the heart that feeds both optimization and synthesis. And therefore, I think if you're going to imagine a world of network design automation, really have to start from here and invest a lot here in understanding how to do effective modeling and how to do analysis for those models for enabling network design automation. So a couple of other points, important points that I wanted to make here was, the first is that now if you focus on analysis, the analysis capability impacts design methodology. So to again go back to this picture here, in this picture, we can do timing analysis and functional analysis separately. If I just give you a bunch of gates and memory elements and ask you, how fast does this run, what does it do? If I didn't have a synchronous timing methodology where I could separate the concerns of timing and function, then I really could not be able to do large designs. So the fact that I can do these separately comes back and influences and gets you to the synchronous design methodology. So this basic idea of separation of concerns is really critical in the sense that it makes life easier in terms of handling one thing at a time. So again, if we look at network design methodology, so how can we maximize this? How can we have a design methodology that lets us deal with issues separately one at a time rather than them getting combined into some horrible multidimensional aspect that you have to handle at a time? Now, again, since the session's about mostly verification, let's look at the analysis capabilities in having an impact on verification. So this in the hardware community, it's well known that reasoning about combinational logic is much easier than reasoning about sequential logic. And as a consequence, this has a direct impact on how we do designs. So in particular, going back to this picture, once we fix the memory locations in the beginning, through the entire design flow that I showed, you actually don't change this very much. And in fact, you don't change this at all. You obey the initial placement and the state definition. And as a result, the implementation verification reduces to combinational logic verification here, which is much simpler. So here's an example of a verification-driven design discipline. So actually, the analysis capability also impacts how you verify, your verification methodology. So in particular, going back to this point where combinational logic reasoning is much easier than sequential logic reasoning, very often it is very hard to completely reason about this complete system. So instead, what you do is you look at a time-unrolled version of this combinational logic, and you make claims or you do reasoning about a fixed number of cycles, which doesn't give you full verification, but it gives you increased confidence that if a k-cycle system doesn't show you any bugs, then there's a pretty decent chance that if k is large enough, that this design is bug-free. So what I'm going to do in the remaining 5 minutes or so is show how this last point that I made about the analysis capability impacting verification methodology. This is sort of the driver of our work where we started looking at network data planes and said, okay, so SAT-based techniques have had a lot of success in hardware verification. How do we apply them in the context of network data planes? So in particular, what we wanted to do was we wanted to avoid state space explosion, which basically with the large state space, which has contributions coming from large packet header size, the large network size with thousands of switches, tens of thousands of switches with thousands of rules, and also the state space that comes because of the concurrency. The packets can get processed at switches in different orders, so this leads to a large number of packet interleavings. So what we wanted to do was we wanted to avoid model checking, which basically does exploration of the entire state space, and somehow try to see if we can survive with propositional logic reasoning with SAT and essentially live in the safer NP-complete part of the world rather than living in the p-space complete part of the world. Now, one thing that made it easy for us is that if you look at the data plane, and especially in the context of network design like software-defined networks, SDNs, so what you can do here is that you can look at the entire network at a single snapshot of it, which gives you a static network state. So the rules and the switches, they're all statically fixed, so that state won't change. There's in the community, this is sort of an accepted sub-problem in design verification, and it's justified because the network state change is relatively less frequent compared to the lifetime of a packet through the network. So that takes care of this part. The network switch state, we essentially make this a non-issue, but we still have to deal with the packet header state and the network state due to interleavings. So what we'd like to do is we'd like to think of the entire data plane as a logic circuit, so this combinational logic circuit here with inputs and outputs. And if we can do that, then essentially these outputs and even this internal signal, so any of the signals here, they're the functions of only the present value of inputs. We're trying to make the problem as simple as possible if we can. And if we do this, we can then represent this network as a formula, which is a conjunction of essentially the transfer functions of all of the switches. This then we can, in a standard way, add to this a property formula, which encodes the negation of what we are trying to prove. Because if this negation ever is true, then we've found a counterexample. So for example, to check the reachability from a point A to a point B in the network, we can define, to this network formula that I showed you in the previous slide, we can define a property formula, which is the negation of this. And then the satisfiability of this, if it is indeed satisfiable, I have a violation of the property with a counterexample. And if it's unsatisfiable, my property holds. Okay? Now, that's what we'd like, but there are some challenges here. So in particular, even if I just limit myself to a single packet entering the network, a link may see multiple packets. So for example, I might have a loop through the network, and in this loop, then the output of this switch will possibly see multiple packets as they go through this loop, or possibly packets from other points in the network. Even in the absence of loops due to multicasting, I might, for example, have a packet come here, and either copies of this packet go through these two different paths, or modified headers, packets with modified headers go through these two different paths. So the blue link would again see multiple packets. So what we wanted was that the switch outputs be a combinational function of the inputs, but unfortunately we see this is not the case. In this case, this is an input-output relation, and here this is a fixed point computation. And this is actually very problematic because what this means is that you need to store sets of values, and from our experience in hardware, anytime you need to store sets of values, that limits scalability very significantly. So here's sort of the adaptation of it that manages the situation. So if you limit your packet flow to a single path for a single packet through the network, then you can actually get back our desired property. So what that means is that in the first picture, you're going to implicitly block the loop. You're basically saying, I'm not going to allow a packet to loop. And in the multicasting situation, what you're saying is I'm either going to consider the top path or the bottom path. Now, that's obviously capturing only part of the network behavior. You're limiting behavior. So is this any good? What's the point of restricting things so much that it really is worthless? So let's go back. Our goal was counterexamples for property failures. We would like to get counterexamples that show failures of these properties. So if we are going to limit ourselves to single packet, single path counterexamples, then what we'd like to see is what is it that we can actually check with this. So actually, the nice part is that this suffices for checking functional properties such as reachability checking, which includes things like waypointing, blacklisting, and so on, because all you need to show if a property fails is one packet as it makes its way through the network. Similarly, properties that sort of go cross-functional and performance issues, things like forwarding loops, you can actually check with this. So I told you that you don't allow forwarding loops, but part of this methodology actually detects the forwarding loop. So the way you don't allow it is by detecting it and blocking it. And then security properties such as slice isolation, where you don't want, and this is in the virtualization context, where you don't want packets from one tenant to sneak into the other tenant. So I think I'm running out of time here. So I'll just be very brief now. So there are a couple of things that you can do in the modeling to actually manage this. So in the multicasting case, essentially what you do is you non-deterministically select either the top path or the bottom path through a choice variable. And this choice variable then gets explored in the solver to generate all possibilities for determining the counterexample. Similarly, for the loop, you do a little bit of just one bit addition into a packet, and then that one bit gets modified in some way as it goes through the network. I'll skip the details. But one very important point that I wanted to make here was that this just one bit addition, it avoids maintaining a full path history, because one of the ways you could check for a loop is just keep track of all the switches that this packet has seen. And if you do that, you're going to maintain a whole list of the entire path. And this completely avoids that. So the goals that we had was we never wanted to store any sets, so we are never going to store any sets. So that goal still stays. So we've tested this empirically. So there's one actually very nice benchmark that's available. This is the Stanford Backbone Network. This is a real network, significant size. And for this network, we can detect a loop in about slightly over 100 seconds. Forwarding loop we can detect in this network. And this is competitive with a technique that actually George has been involved in. So this is very competitive with that. And it uses a very different method. It uses ternary symbolic simulation. And then to look at scalability, we followed sort of the standard methodology in the verification community by building some synthetic networks. And I'll just show some results here. So this is a check for a forwarding loop. And the sort of main, so this is for the two different methods, the SAT-based method, header space analysis, different header sizes, for a fixed net number of switches, but changing number of routes, which changes the number of rules in the switches. So roughly what we see is for both methods, there's a sub-exponential growth with the number of routes, and there's very weak dependence on the header size. And at least for this particular example, this particular property checking and this class of benchmarks, the SAT-based method does better than the header space analysis. And this actually, the scaling continues as we look at larger sizes of networks. If we look at reachability checking, actually the roles get switched. Header space analysis does a little bit better, but again, we sort of see sub-exponential growth with the number of routes and low dependence on header size. So the last point I'll make here, and maybe I'll just take less than a minute here because I can see anxiety at the back here. Once you have analysis, you can actually do synthesis. And I won't go through the details, but in particular, the fact that you can check, for example, the equivalence of two firewalls using SAT-based techniques, you can then plug this into a method where you can build something that's a symbolic firewall with k rules, add some symbols. This is an idea that sort of even is used in program synthesis. And then using the same equivalence checking method, what you do is you ask the question, is there some symbolic firewall here that for some assignment of rules, some assignment of these rule symbols can actually create a firewall that's identical to the firewall specification. That is, there's no difference in the outputs for these. So this translates to a more complex formulation. This is a quantified Boolean formula. And in practice, this tends to not scale very well. But the key point here is that at least we have, based on the analysis technique, we have a systematic way of formulating this problem. And now we can devote some attention to actually building solvers that can help crack this. So this problem, by the way, shows up in different forms in software synthesis also. Okay, so I'm going to just stop here. I just want to put up the main points that I put up in terms of ideas from electronic design automation that I think we need to have in a conversation about network design automation. design discipline, design flows and abstractions, effective modeling and analysis, maximizing separation of concerns, and in particular, this last point, which I touched upon with the work that we've done, that is how your ability to analyze can go back and influence how you go about verifying things. Okay, I'll stop, and I don't know, I suspect we don't have time for questions, but I'm happy to take them in the end.
Thank you. Thank you very much.
And let's set up George, but in the meantime, there's could be time for one or two questions, and we should use the mic for questions. Yes?
One point you made about like what's the driver for network design automation might be if complexity is not growing. I think so a couple of things. I think, but at the largest end of the spectrum, like Microsoft, Google, Facebook, the complexity is growing.
No, complexity is growing, but I don't think it's holding people back. I think people's existing methodologies are.
Right.
It's not holding them back.
So what really holds, so my point was going to be, what really holds us back right now, it's not so much the growing complexity, but the agility that is basically, I think, the driving force, at least some of the work that we end up doing is like, if the network's very complex and hard to reason about, then people are fearful of making change. So unlike hardware, these change requests for the network, they come in all the time. So I think for a lot of the driver for some of the work we do is like, can you safely change your network, which needs to change every day?
Got it. Yep.
So that's kind of agility is a driver, yeah.
Very valid point, yeah.
So, okay. Where's the switch to? This is forward. Oh, I see. Okay, perfect.
So thanks again. And George, we get the mic. So the next talk is by the puppet master.
George, a dear colleague who has, I work closely with George on network verification, and he will cover the topic of what he coins as NDA, and don't worry, you can talk about it after leaving the room. So.
All right, I'd like to take the next logical step after Sharad's talk and try to see how you might move from the lessons learned from EDA to what we might call network design automation. Okay? So in order to do that, I have to show you, especially if you're not in networks, why reasoning about a network might be hard. So a router is just a box that maps something called prefixes to ports. So for example, that router, that box, has two prefixes, all destination address starting with 10 and all destination address starting with 1. And a packet, the box on the left, arrives starting with some set of bits. It's actually a 32-bit IP address. And now this packet matches both these rules, and the longest match is the first one, so the packet should be shipped out to port 1 on the top. So it's so simple, and that's the original internet, and it is not very hard to reason about. Okay, so many things have complicated life. The first thing is load balancing. Okay, because links are running out of gas, people nowadays don't just send it to one link, they load balance it across a set of links, and most of that is actually chosen non-deterministically using some kind of hash function, which is known only in runtime for reasons that I don't want to talk about. They're horrible, but nevertheless. Okay. Now, that by itself is okay, but then an additional thing that a lot of people do, I think I better heed Sharad's lesson, and is that they go ahead and for security reasons, they allow network operators to add these manual rules called access control lists or ACLs. For example, it's very reasonable, given the slammer worm, to be able to block packets that contain SQL messages, right, which are indicated by another field, which is called SQL. So the manager might decide to say, on port P2, block all SQL packets. The difficulty is that it interacts with load balancing, and it's not clear which set of headers are actually blocked when they're going to which destination addresses, and it depends on the load balancing function. When it switches, as Jeff will talk about, then stuff changes again, and so it is kind of messy. Now, besides this interaction between load balancing and ACI and manual rules, the situation is exacerbated because we have lots and lots of forwarding protocols, lots of vendors with all the idiosyncrasies, Broadcom, Arista, and ultimately it's these manual things that people have to do to keep networks working. And we only have these crude tools. Okay, so simple, basic, reasonable questions are hard to answer. Which packets from A can reach B? That's Sharad's reachability question. can we sort of isolate students from faculty, or at least the grades? And and we'd like to kind of show these kind of isolation things, just like in operating systems. And then when your web server is, my web page is taking too long to load, is the problem the server or is it the network? And this is a traditional finger pointing exercise. And we also, as Microsoft and many other companies like Google, we have a bunch of data centers linked by a very expensive, precious backbone network. Okay, and we care a great deal about the utilization of that, and we want to know why these traditional protocols are utilizing them poorly. We have load balancers all over the place, and sometimes they don't quite distribute packets evenly, and you'd like to kind of figure this out. And ultimately, another horrible thing in our data centers is mysterious packet losses, and we really, really want to know where they are and why they're occurring. So what the world is crying out for is a set of tools to do a bottom-up analysis of just existing systems without waiting for the misty future. So is there a motivation to do better? Yes. Okay, so we know from our internal networks, and I will spare you the details, that we get a lot of errors caused by manual stuff, and some of them are externally visible. Now you might say, oh, Microsoft, they don't know how to do anything, right? But on the other hand, we've done these surveys, and we found that everybody has this trouble, including Google, right? They actually admitted it. Matt Welch is very indiscreet, and so he admitted it in a blog, which is useful. And Sharad is looking for a driver, right? Why now? Why didn't we do this 10 years later? And I think one driver, besides Ratul's agility driver, is that we are moving now to the services market, right? Take us, for example, right? Why would our CEO care? We used to keep Office, our crown jewels, on disk, and we would sell that. Now, increasingly, we are moving it to the services model. So if the network is down, we are going to lose a major fraction of our revenues. So suddenly, it's an issue that CEOs care about, right? It's not a nice to have, but it's a must have. All right. Now, so that's networks today. But what about tomorrow? As we move to services, it's going to occur to a lot of CEOs, let's optimize our private network, our data center network, which is a computer after all, to reduce latency and costs. That wasn't possible till a few years ago, but it's just becoming possible. For example, merchant silicon is available today cheaply with vendors like Broadcom. You can build your own router. And the rise of data centers, the data center is like a big computer. It's a bunch of small computers connected together by network. You can do what you please within that network as long as you talk IP to your customers. And also there's software-defined networks that allows you to program these routers. Okay, so all the opportunity is there, but if we couldn't even design these static networks in the first place, how in the world are we going to design these brand new networks, right? And so that is crying out for what Sharad said as a design methodology, which we would call, which is really going to be more about designing networks and synthesizing networks to optimize some goal. Okay, so those two sort of intellectual themes I'm going to weave through this talk. And before I do that, I want to put up this slide, which on the slide on the left is something that my friend Nick McKeon sort of first drew, and this analogy he made between EDA and NDA. And it just starts with the things like Sharad talked about, a standard functional description, and it ends up with layout and finally post-silicon debugging. So I want to go a little further and just wonder what the corresponding tool chain might be for networking. Don't get too hung up in the details. It's just misty. It's a little mystical. It's a vision, right? But just look, corresponding to RTL, we might need a policy language. Corresponding to things like post-silicon validation, we might need debuggers and dynamic checking. And corresponding to test benches, we need test package generation. And in between, we probably want layers of analysis and layers of synthesis. Okay? So that's the model and the kind of vision that's animating a lot of work at MSR right now. So accordingly, I want to give you a flavor of these two strands of work, a little bit on verification, which is mostly about analysis via symbolic execution, and then a little bit about automation and a few interesting problems based on synthesis. All right. Before we do this, okay, we have to confront this grubby reality that we have tremendous diversity. Whether it's a Cisco box or an Arista switch, they're all so different. How in the world is a tool industry going to be born? What saves us is that, in essence, there is something in common. Okay, so you already know a router. It just maps a bunch of prefixes to ports. There's another animal called a bridge. It doesn't matter what it is. It takes 48-bit Ethernet addresses and does an exact match on them and maps them to ports. There's another creature called an MPLS switch that uses small integers called labels and goes ahead and maps them to ports and sometimes sort of plays with these labels. And now, while they all look different, and they all come from different vendors, fundamentally they all match on some fields and basically do some actions like rewrite headers. Okay? Now that's the essential insight for something called OpenFlow, which you might have heard of, which is a design movement for future routers. But what we'd like to say is that besides it being used prospectively, we can use it retrospectively to understand existing networks by mapping them to this intermediate form to generate tools. Okay? And so that's the essential insight behind behind this thing called header space. So you start with this router, and it's basically at the low level that Windsurf would see. It's a match and an action, and you do this. But you could think of it a little more abstractly as a header space, and the rule that is matching is a hypercube in this header space. A packet is a point, and what the router is doing is basically mapping points from one space to another. And with that, what happens is the Cisco forwarding table or the bridge spanning tree table now becomes a set of guarded commands in classical Dijkstra notation, where one subspace maps to another and a sequence like that. And if that's the case, and you can compose all these routers to make a network program, the entire network of boxes and fiber optic links becomes a big program. So now you should ask the question, why can't we apply every methodology known to man for programming? Debuggers, static checkers, runtime checkers, specification mining, every idea known in the last 20 years, why can't they be applied here? And that's what's exciting us. All right. So basically, to summarize, the header space framework is going to take all these routers and summarize them by a transfer function that maps sets of headers to sets of headers. So what can you do with that? Well, now you can do symbolic execution. So imagine you want the simplest question, A talking to B. So what you can do is start with the complete space at A, right, which is the entire possible set of packets, and pass it through the transfer function at the first router, and the header space splits up. And you're keeping track of sets, as Sharad said. And now you keep doing that. And finally, those spaces sort of move through these transfer functions, and they emerge at B. Okay? And formally, they're just a bunch of compositions and unions. Now, unfortunately, that's not quite enough because the packet could have been rewritten. So you need to do one more step to invert the spaces to figure out which packets A must have sent. So as long as you have a compositional and invertible semantics, all this stuff can be done. And you can do all kinds of other things like waypointing and general questions like this. So two big takeaways. First, remember that from the point of view of programming languages and model checking, this is just symbolic execution. The real essence here comes in the domain-specific data structures. We don't just use BDDs or throw it into a model checker that can give us big wins. Second, remember, it's abstraction. We've taken all these real boxes and written real parsers into these transfer functions, and now we can stay at this abstract intermediate form that enables tool land. All right. Similarly, the lens that basically says that we can treat a network as a program suggests why not apply the testing lens? People are used to generating inputs in order to maximize coverage for testing. Why not do the same for networks? So we've done this briefly, right? And there's some differences and nuances. First of all, we're not so much into correctness, but we want to test performance. How are links doing? Are we dropping certain packets? And so the notion of coverage doesn't become line coverage or function coverage, but covering every link or every queue or every rule. And we can see that it becomes better. Now, for those of you who know about test generation tools like Dart, Patrice is here, or Clee, what's different? It's actually much, much simpler. We don't have cycles in normal cases, so we tend to have a finite graph, and so we can throw in very simple set cover, so the intellectual problem is actually reduced, right, compared to the standard problem. Now, when we did network verification, as Sharad talked some of these answers, when we did them for a single pair, we got numbers like a second. But we have hundreds of thousands of stations. And if we start doing that for all pairs, today the numbers traditionally are about a day. Fortunately, there is design discipline in all these modern large networks that makes life better. We tend to design things according to structures, right? Just like people design these chips in very nice systematics, we tend to design them as these fat trees with backup routers arranged in certain symmetrical configurations. So, if, for example, there's symmetry in almost a group theoretic sense, where if you interchange these backup routers, life is roughly the same. So it's modular, so you can kind of do these quotienting tricks that people have kind of done before in model checking, but these are based on physical symmetries, not symmetries on the logical crypty structure. Further, so Gordon Plotkin, who's one of the world's leading logicians, is visiting us, and he's worked with us to create this new semantics that basically has the simple symmetry theorem that can reduce these large networks to simple networks with equivalent behavior proved by something called bisimulation, and now we can do verification cheaply. But further, this design discipline also has something like a standard cell. You have these stamps that we put out in order to deploy our clusters very frequently. And his semantics also has a modularity theorem that allows us to reuse things and parts. And lots of networks are built this way. So we're kind of excited by using these things. All right. So far, I've talked about data plane verification. But there is this very nice tool, has nothing to do with me, but Todd is here, Ari is here, and Ratul is here, and I don't understand it well enough, so I'm going to say only 3 things about it. First of all, it's about the control plane. Remember that so far I've assumed that there are these magical forwarding tables, but who built them? This is a routing protocol. That's the control plane. There are bugs there too, waiting to happen. For example, you could have backup routers with bugs, and if you don't do it right, when they come on, they're going to cause trouble. So what these guys have done is actually built an analysis of that, right? And there's a key abstraction they have, which sometimes is sort of not seen. They basically ignore the timing parts or the race conditions. They just model the fixed point of the routing protocol, and they look for bugs that they can find based on that. Still very useful. Ari is going to demonstrate it tomorrow morning. So if you guys want to see this in action, please watch it. Okay? So I'm going to ignore their toolchain. So sorry, guys. There it goes. All right. There's lots of other work, starting with Jeff's sort of pioneering work, right, which he's going to talk about, and ending with Netcat and other stuff that David's going to talk about. But I especially want to mention a lot of work in UIUC on Antiter and Veriflow, where there's a lot of work by that group. All right. How am I doing for time? 5 minutes? All right. OK. So all that part rushed through was about analysis. Okay, let's take a deep breath and wonder what synthesis might be like. Okay, so it's a bit of a moonshot, right? Can you imagine telling networking people, in 5 years, we're going to generate all your Cisco config files from a specification, or even better, we're going to generate a specialized TCP for you from a specification. It sounds crazy, but what the heck? They're all professors here, so let's shoot for the moon, okay? So, but I need to move a little back. All right, so again, what we've talked about and what people have done in this room and others has been mostly on verification. And now we want to talk about things like synthesis and maybe debugging. All right. Sharad said that one of the great things about EDA is it allows you to specialize things, right? You have specialized components. We really want to do that, Sharad. We want to do that for our backbone networks. Those backbone networks are so precious. We want to literally pack all the traffic flows that go in there to maximize their usage. And we really dislike the traditional routing protocols that kind of do this hit or miss kind of thing that really leaves for 30 or 40% on the table. Okay? So Google's done that, we've done that. And so to abstract this problem in a slightly interesting way, there are 2 transitions going on here. First of all, I'm moving from reachability, whether people can reach, to actual quantities, performance. Second, I'm going to move to probabilistic models, which is also interesting. Okay, so to motivate this problem, imagine there is this very expensive 3 gig link in the middle. And there are 4 data centers, A, B, C, and D. Only A is talking to B in this simple example, and C is talking to D. But they have a probability distribution. Whenever A sends to B, it sends mostly at 1 gigabit with 90% probability, but occasionally with 10% probability, it sends at 2 gigabit. Now, traditionally, we like 95% confidence. So what a lot of people do, our managers do, is they say, well, in that case, we'll summarize the A to B traffic as being 2 gigabits, because that's what it needs to cross 90%. Similarly, we do that for the C to D traffic. But in that case, it can't fit in to this little knapsack of 3 gigabits per second, and we have to reroute some of the flows. However, you will of course have noticed that the only way you could get to 4 is if both A and B send at 2, and if the probabilities are independent, it's 0.1 times 0.1, which is 0.01. So with 99% probability, if we could analyze the probability distribution, we could pack the distribution better. So this is kind of an interesting new optimization idea, right? And it's something that we began with folks at Berkeley, like Garwith, but abstracting it very simply, it sort of suggests a completely new optimization problem, right? So imagine the traditional knapsack problem. Now, instead of pieces, you have distributions. And now, instead of the traditional correctness of fit, you want to make sure to pick a subset of the input distributions such that the convolution of that subset is less than some specified failure probability, say it's 5%. And subject to that correctness spec, you want your liveness spec, is performance, you want to find the subsets that minimizes the expected waste or maximizes the average packing in the bandwidth link. Okay? So this is a very nice problem, and it's sort of I think it's exciting a lot of people who so we're working on it with a bunch of people, including Dick Karp and Ravi Kannan, and so we have some initial results. Okay? So it is clearly at least as hard as knapsack, and it's probably a little harder. Now, there's a ton of other. This is just a flavor of a new area gives you new optimization problems. If you're a theoretician, you should sort of be excited, right? So there's a ton of other synthesis problems. You could synthesize rules, right? People have done this before. Synthesize virtual networks. Jeff has worked on it. Sanjay has worked on it. You could synthesize tables within a router. And you could even, heaven forbid, synthesize a specialized transport for your own good. And that is a kind of a remarkable thought. OK, one last slide on debugging. And then I'm done. OK, so everybody likes, I'm a terrible programmer. I love the ability to step through my program. When I'm in trouble, I say, what the heck did I do? And I love what is the equivalent of step and watch for a network? Now, there have been network debuggers, but they've been kind of batch debuggers. It's like bunches of printf statements, and then you kind of mine them to figure out what's going on. So it turns out that, I don't want to tell you too much more, that working with some really good hardware designers at Cisco, we kind of have some idea of something like a step, which can give you the real-time sort of fate of a packet, where it went, what time it went in microseconds, right? And you have to do that efficiently without breaking the hardware pipeline. So it's not that straightforward. And it's kind of like a new incarnation of the old traceroute with real-time behavior. And how it's done efficiently, I won't tell you, just tease you with it. So if you really want to know, I'll tell you the idea later. Okay, it's very simple. All right, so I'm ready to wind down. My biggest message for you is that there is all of these ideas that we have talked about are old. And you must be wondering, can anything new come from Nazareth, right? We've seen all this before. We've done symbolic execution. We've done testing. I've done all this. These guys are merely reusing all this stuff. The thing I want to beg you to reconsider is no. Everything is in the domain, right? The domain has differences. For example, in the formulas we have for networks, as Sharad will talk about, we have limited negation, almost no loops in practice, and supposedly as long as there's no bugs, and very small number of equivalence classes. We have even found it easy to do incremental verification, which is kind of a frontier task in real verification. Why? Because we have a network graph. It has a very specific structure, and it's easy to keep track of that structure. It's kind of, we didn't know it was hard, and it was doable. Test generation, if you look at tools like CLI, and they go through all and Dart, and they go through Sage, they go through all kinds of effort because they have the state space is so large, they have to use heuristics to figure out how to maximize their coverage. We can cover the state space. It's not hard because there are no cycles. And finally, symmetries, right? Gordon's work on symmetries, people have done it before in model checking, but they are doing symmetries on the logical structure, the Kripke structure. We are doing symmetries because the physical topology is symmetrical, right? The backup routers look identical. And it turns out, again, in the domain, as Gordon would always point out, there are differences. There are nuances in the state spaces, headers and locations, and those symmetries are very different from the Sisler-Emerson kind of symmetries. Okay? So there's a whole new world here. There's an intellectual opportunity, and we welcome you to join. Okay, so summarize my points. This is an inflection point, right? The rise of services, maybe the need for agility, is going to make some of this, I think, essential. And data centers and software-defined networks are enabling technologies that make this possible. I think there are ideas here. Symbolic execution and analysis specialized to the domain, and optimization, again, specialized to the domain. So the first one for analysis and the second one for optimization. There's an intellectual opportunity. You get to rethink. I have this sort of somewhat dangerous contention that give me any paper in any interesting idea in programming languages in the last 10, 15 years, whether it is, and I think there's a way to kind of retrofit it with interesting changes, mutatis mutandis, to this new world. So it's a fun thing, it's join the party. But I think there's also a systems opportunity, right? There's working chips today with billions of gates. Why not? Why couldn't we have these large, agile, completely easy to reason about operational networks next? And that's the thing that's exciting us. Okay? So it's a long shot, and who knows if it'll happen in our lifetime, but it's something to aim for. Thank you.
Thank you. And questions?
Yes.
Hari.
Yes.
10 years to the correct date on the paper is actually 10 years in the future from what you wrote.
Say it again.
No, I'll tell you offline.
Okay. All right.
It's from 2004 or 2005. 15 years. Okay.
Oh, the date on the paper was wrong? Your paper? That's Ratul's problem. I'd like to blame somebody else. Yeah.
Hi, George. I did not quite understand your comment about symmetry. Do you mind repeating what your argument there was? I understand that data center networks are symmetric, but I may have missed that part of it.
I went very fast. Okay, can I tell you it again? Okay. So roughly speaking, we would like to see that if we interchange two routers, right, and you make the right changes in the headers and the rules, right? So you have to give me we have a certain set of transformations. And everything stays the same. The questions we want to for reachability stay the same. So given that, right, as a setup, which we need to prove, we can transform the original complex fat tree network into a thin tree. Why does that help? Because we have less routers and less rules. Assuming that verification scales with the number of components, we get speedups of 100x. That's what we get. Okay? So suddenly what used to take days is now taking us hours.
And here you're talking about data plane verification specifically.
We're taking only about data plane verification, but we're talking about real ones. We're talking about our large data centers. So we're not talking about toys. It's not talking about Stanford. We're not talking about little thing, synthesis, the real stuff, right? And comprehensive, all pairs between every set of predicates done and the goal is to do it in a few minutes. And I think we can. Yes. Yes.
So I'm primarily, I guess, asking in terms of more runtime verification. So one of the things that operators care about a lot is impending failures, right? So that if you think in terms of how the state is getting transformed as the traffic is going live, something that's going to fail in the next 30 minutes, an hour or so, something that they can essentially track or at least get a heads up. So I'm wondering if all of the first two talks I heard were probably more geared towards static verification. So let's check reachability, let's check load balancing, which are more static properties. I'm wondering if have you any thoughts on?
Totally. I think that's I only talked about debugging, but runtime verification, a set of tools is essential, I think. And things like yours, I think there's been a lot of work, but to put it into this framework, try to make it work together with these other things is important. So totally, I didn't mean to ignore it, but there's only 20 minutes.
Okay. Yeah. So with that, let's start the next talk with Jeffrey from the Naval Postgraduate School, Monterey. Jeffrey made early foundational contributions in network verification, and he will talk about abstraction-driven network verification and design.
Thank you. Good afternoon. So today I'm going to look back some of the internet routing research I performed over the last decade, and share with you some of the lessons learned and observation on leveraging abstractions for network verification and design automation. So it all started when I spent a 1-year sabbatical at CMU. I joined a group led by Hui Zhang, and including Dave Maltz and Jibing Zhang. And I was fortunate to be involved immediately in a very interesting project with collaboration with several AT&T lab researchers, Albert Greenberg and Jennifer Rexford and Gisli Keon Tyson. So our goal is to reverse engineer a large set of networks managed by AT&T, trying to understand their routing designs. Apparently, some of the networks constantly experience outages due to routing anomalies, forwarding loops, and black holes. So we are given what we have. We have the router configuration files. So here is an example of a router config files. For those of you who have worked with routers, you immediately recognize this. And it's not unlike assembly code. And it defines the interfaces. For example, in this very simple example, it defines 2 interfaces on this router. And also, it defines routing protocols to be run on this router. So here are the 2 routing protocols, OSPF and BGP. And more importantly, there's a lot of policy defined in this using these very low-level commands. So for example, there are some packets that are being filtered in one of the interfaces, and there are some routes being shared between the routing protocols, but not every route is shared, only some of the routes are shared. So these are all policy decisions that the operators can apply, and that will impact routing design. So clearly, those low information, that's just one router. In the networks we studied, actually, some of the networks have hundreds of routers. Imagine all these files. If you do it manually, it's impossible. So that's why we want to develop a reverse engineering methodology to automatically extract routing design from the configuration. So here is an example of a 900 router network. And the files, the router configuration, largest router config files they're sorted based on the number of lines in the config files. So you can think the largest router config has close to 2,000 lines. On the average, they have more than 100 lines. But nowadays, some of you probably already have new data that shows some of the router configures even larger than thousands of lines, can be 5,000 lines, 5,000 on average. So that's more recent data. So after some digging, so we're able to develop a reverse engineering methodology. So first, we use the router configuration files. We're able to infer the logical IP topology. So this example, for example, we can infer there's an IP connectivity between this set of routers. And then by mining the interface information. And then we mine the routing protocol configuration information to construct what we call a routing process graph. So each router can run one or more routing process, each one corresponding to a new protocol. So most routers run one process. But some routers, like they are serving as a glue for multiple routing domains, they can run multiple routing processes to glue different routing domains together. So in this example, there are 2 routing domains. So after we construct a routing process graph, we notice that this graph can be huge, right? Several hundreds of routers, then you have several hundreds of processes at least. So it's not going to be scalable, so we develop an abstraction to make this methodology scalable. We basically collapse all the routing processes that share complete reachability information. That means there's no policy between them. There's no route filtering between them. We collapse them into one single routing instance. So in this case, we're able to reduce this routing process graph in this very simple routing instance graph. So by doing so, we're able to extract the large routing structure of the network. So we apply this methodology to 30 production networks, mostly medium to large size, transit and enterprise networks. So we found a very interesting, we found that the routing designs in the wild are much more diverse than the textbook model. So what is a textbook model? So this is a textbook model. So usually the text model describes a network for a company as such. The company runs an interior gateway protocol such as OSPF or ISIS. Then the companies use BGP to connect to each other. So this is the standard textbook model. But after we run the tools, we found that most of the networks actually are not conforming to that model. So here is an example network that we are able to model. So you can see there are a lot more routing instances run by this network than just a single IGP. Not only that, a BGP, a traditional interdomain routing protocol, is also sometimes used within the enterprise, used within this network to create a compartmentalization, local compartmentalization. So the takeaway here is that the network can have many routing instances in the wild, can have many routing instances, and while we have very good understanding of routing protocol at that time, we have very good understanding of routing protocols such as BGP, OSPF. We did a lot of study on that to make sure they are safe, but there's very little understanding at that time of the interaction of these routing protocols. So in fact, the subsequent studies, oops, they're missing. Okay, here, okay. So the next slides, I want to show you what the mechanism actually, in fact, the mechanism governing these interactions are not defined by the IETF. They were invented by the router vendors as software patches. So the first routing mechanism is called route redistribution. So I want to show you, illustrate this mechanism using this very simple example. So here there are two routing domains, and B, again, run two routing processes to serve as a glue of the two routing domains, to glue the two routing domains together. So here, this is the picture shows the routing process run by router B. And when a route is advertised from the left domain, which is a RIP domain, by default, the router in a different domain, the OSPF domain, will not be able to see that route advertisement. In other words, the two networks are separated. Okay? So by configuring route redistribution, you can address this problem by configuring route redistribution on router B. So this is route redistribution using this command. So this is a configuration command that's enable route distribution. By using this route distribution, the routes from the RIP domain will be injected into the OSPF domain. Now the two hosts on the two networks can communicate with each other. And the second mechanism is called route selection. Now, why is route selection required? Because as we're seeing, that some routers run multiple routing processes. So they will offer, multiple routes were offered by different routing protocols. How do you select a route between these routing protocols? Because different routing protocols use different types of metrics. RIP use hop counts, OSPF use an integer cost function. So route selection is required when you have routes coming from two different protocols. And again, router vendors introduce this as a software patch. They basically introduce a universal metric called administrative distance to arbitrate between routes from different routing protocols. So let me show you this example. So in this case, D, another router that runs multiple routing processes, will receive two routes. One comes from the RIP route instance, and by default, it has an administrative distance of 120, and OSPF will receive a redistributed route from the router B, which has an administrative distance of 110. So since 110 is smaller than 120, so in this case, the router will install the OSPF route. So the operator can over that default AD value by using a simple command called distance 90. In this case, it will make RIP routes more preferred to the OSPF routes. So these are the two mechanisms used nowadays for routers to exchange routes between routing protocols. And the subsequent study have confirmed that these two mechanisms have major impact on routing safety. And I want to also say something about SDN. So SDN, by logically centralizing the control plane, eliminates some of the problems associated with distributed routing protocols. However, it still have this issue of multiple control functions competing for the forwarding path. So recent work has shown that this kind of problem can still occur, the conflicts between multiple control functions. And the problems can be even more complicated in a hybrid networks when the network is partially migrated to SDN. So now you have to deal with both distributed routing protocols and a centralized control plane. So after we've done the reverse engineering work, we move on to a core question in network verification, reachability. Basically, we pose the question, can we mine sufficient information from the configuration files in order to predict reachability when and whether or when two hosts can communicate? So the state of art at that time was build it and test it, basically leveraging the probing tools such as Ping and Traceroute. So this kind of probing tools have major shortcomings, as I will illustrate with this simple example. So this enterprise has 2 sales offices, and there are certain accounting machines are only allowed to communicate with a server in the central office. So here is the common practice is that install a packet filter on the links to implement this very simple policy. Now, what if the network designer want to add some resilience? Okay, add some resilience, and so in this case, these 2 links are deployed, and they configure the routing protocol to use the links when the primary links fail. Okay, so a common practice in the network community is that in the operation is that to use template-driven configuration, basically copy existing configuration to the new links. So in this case, he will copy the packet filters from the existing links to the new links. So everything works great because testing will not find any problem because when there's no link failure, packets still traverse the primary links. Everything works. But when the actual failure happens, the packet will traverse the backup links, there's an issue. Because you can see this link doesn't allow the packet from B to go through this link, and the packet will be dropped. So how do we solve this problem? And so we're able to, after some digging, we were able to find this abstraction called the reachability set to model the reachability requirements. Basically, reachability set is a set of all packets permitted from one network location to another network location. So it's naturally a packet filter or access control list can be modeled as by a reachability set. So for example, permit AC is just a simple predicate to find all the packets meeting that predicate. The effective routing protocols can be added as a dynamic destination address-based packet filter because if a packet does not allow to route to the next node, it will be treated as a reject route. If it's allowed, then it's permit. So here, by simply using an intersection function, we can model the behavior of routing protocols. How many minutes? How many? The packet transformation also can be modeled as a generalized conversion functions. So by doing that unified modeling, we're able to create what we call a reachability analysis graph. So each edge just associated with one composite filter, taking effect all the packet filter configured on the interfaces and routing protocol effects and packet transformation gateways. So by doing that, we're able to infer reachability along a path. For example, you have reachability along this path will be in this set intersection of the 2 filters. we are able to also compute the reachability sets among multiple paths by simply using the set union operation. So let's go back to the old example. So you can see that with the reachability computation model we developed, you're able to, the operator, without deploying the new configuration, can make this, can do this derivation, and the operator will find out the reachability from B to C will be affected by this, without be correct, because the reachability set will become empty. That will indicating there's a reachability problem, and then the simple copying of filter rules will not be sufficient. Okay, so how many minutes do I have? Minus one? Okay, so I'll wrap up. So the work has since been generalized in several ways. The most notably, the Boolean satisfiability formulation in 2011, had a space analysis, George and others, in 2012, and also more recent work that a group in University of Texas at Austin developed very fast algorithms to do reachability analysis. They're able to check reachability for most networks under a minute. Okay, so I guess I'm going to skip some of the slides. And so we also applied the similar abstraction to design. We call synthesis. And so we're able to, this is the work we jointly done with Sanjay Rao. And so we're able to use the reachability set abstraction. We're able to automatically create packet filter placement algorithms so that given a set of reachability requirements, which model as a reachability matrix, we're able to automatically determine which interface to place the packet filters and what type of packet filters to be placed. All right. So to wrap it up, so I think with the following observations that I still think there's a huge semantic gap exists between network service objectives and the actions of individual protocols and the nodes. So software-defined networks clearly elevate the level of abstractions, but on the other hand, they also introduce a new type of nodes and still allow diverse control application to impact the forwarding plane simultaneously. And so that can create still the semantic gap still remains. So I argue that we need some higher level abstraction to contain this, what I call curse of many knobs, as we need to make sure that the design space is constrained so that the design can be carried out. All right, thank you.
Thank you very much. So please ask questions while we set up. We are running a little bit short of time, but Nate promises to speak very fast.
I just wanted to say that I think many years ago, like 10 years ago, when this was not fashionable, Jeff and Hui and all the gang at CMU, including Dave Malls, our own Dave Malls, worked on this. So it all started with this kind of work. So.
It's in the folder. There it is. I have the clicker. Is it a PDF? It is. Here are two. Can you help us get the PDF up? We don't have the projector view of the PDF. Okay, great. So I've been asked to take my carefully tuned 22-minute talk and deliver it in 4 minutes. So I apologize for if I skip some slides or talk like an auctioneer. I guess this is a proof that the probabilistic knapsack problem is hard and reasoning about quantitative properties is hard.
So I want to talk about some work we've been doing on sort of taking programming language techniques and trying to apply them to networks. This is completely in line with all the talks we've seen and really builds on a lot of these seminal efforts like Jeff's from a long time ago. So we've seen that networks are important and getting big and hard to manage, and yet somehow network operators seem to do things well. They have a bunch of really cunning tricks that they use, and for the most part, networks are pretty reliable and sort of run well. And I think Ratul put his finger on it when he said, the problem is not getting them to work, it's that they're really not very agile. There's kind of this crazy bag of tricks that are used to generate configurations, to do monitoring, and to debug faults. And so people get kind of conservative, and it's hard to think about making big changes in networks. And so what I want to advocate is that if we want to move to this vision of kind of an NDA world, that we need to find some of these abstractions that Sharab was talking about, compositional programming units that we can sort of work with in isolation, make them do something complicated, plug them into a bigger system, and have everything work. And so we've been sort of trying to do this using programming languages as the vehicle for developing these abstractions. And so our basic methodology is, try to design some languages, try to study their semantics, often from many different perspectives, so looking at logical semantics or operational semantics, and then build tools that leverage those semantics to do useful tasks. And like the other talks, I'm going to focus not on quantitative properties, but on just reachability properties. Unlike some of the other talks, instead of looking at sort of machine models, I'm going to focus on what I'm going to call programming models. So the difference here is that instead of kind of thinking directly about things like pipelines of hardware forwarding tables, I'm going to just, from the start, think about mathematical functions on packets. And so that's what I'll be working with. And if you kind of start from first principles, and this is very much not the way that we discovered the system I'm going to show you, but it's kind of an attractive way to tell the story. There's kind of two things that a network does. It has to classify packets. So you have these big tables that have rules, and their job is to sort of separate all the incoming packets into different bins. And then those packets get forwarded along different paths through the network. And if you take these two key features, classification and forwarding, and you try to design a little programming language that would do both those things, I think you end up with something like this netcat language. And basically what it is a Boolean algebra, which just gives you a way to describe predicates, smashed together with a Kleene algebra, or a little language of regular expressions, which describe paths, plus a couple of primitives for describing how packets get modified and moved through the network. And so this combination of these two Boolean and Kleene algebras has been studied before. My colleague Dexter Cozen's been working on this system for about 20 years. And when you put them together and interpret them as operating on sets of packets, you get this new system that we started looking at a couple years ago. And this is a core language, so it's really not trying to handle Cisco iOS, but you can encode lots of other things on top of it. So it's really trying to distill down to the essence sort of the basics of these packet processing functions and how they compose and work together. So conditionals, for example, can be desugared into a slightly more complicated program. These things all describe functions. I won't take you through this, but here's a picture of sort of how the path concatenation or sequential composition operator works. So packets come in, they get run through the first part of the program, that generates a set of output packets, and then those get piped through the second program, and then you get a bigger set of output packets. And the other operators are all similar. So, losing the bottom of my slides. So in addition to cramming my talk into a small number of minutes, you get to see 80% of my slides. Actually, I think we just have a alignment problem. OK, so one of the neat things about this language is you can use it for programming, and I'll tell you about that, but you can also use it to do the kind of verification we've seen in Jeff's work and in header space and other frameworks. So one thing that you can do is you can basically take these hardware tables and you can just treat them as programs, as George said, and those are just programs in our language. You can also take the structure of the network, so all the links in the topology, and you can represent those as a different program. And then you can kind of take these things together, and you can actually model in the language the iterated processing that's done by a network along any number of steps. So you can kind of start with the program that just does the processing by all of the devices. I call that policy. Then you can look at processing that happens with policy with topology in the middle, then policy again. That's the second term. And if you take the limit of this, you get the term on the bottom, where we have any number of policy topology interleave steps. And so this gives us a way to model the reachability behavior of a network as a term in our language. And once we've done this, we can start to do verification by reducing questions of interest into equivalence problems. So this is kind of a very well understood approach in verification, where if you have an expressive formalism that can serve both as specifications and as implementations, and you can decide equivalence, you can play the verification game by doing various constructions and then checking equivalence. So to do things like check reachability, in this case I want to ask the question, does the network forward all packets received at some ingress to the egress? I can construct my network model, that term on the left, and prefix it and suffix it by the ingress and egress, and then just ask, is this thing the same as a program that just forwards directly from somehow teleporting packets from ingress to egress? And if that's true, then it does the required function. If not, then it doesn't. And lots of other properties like access control policies, isolation, loop freedom, black hole freedom can all be reduced in this way. The cool thing about doing this from the perspective of a programming language is we don't need to necessarily design custom new decision procedures in order to solve these verification problems. So we can actually study, using the semantics of the language, what equivalence means. And in the case of Netcat, there's actually a complete custom deductive system, this little proof system characterized by these few dozen axioms that completely capture equivalence. So I won't step through these. We would be here till 3 p.m. But these capture sort of natural things like the concatenation operator is associative, distributes over union the way you'd expect, and for the packet operations, modifications and test a packet sort of behave the way you'd expect. So modifying and then testing a packet, the same as just modifying it 2 modifications in a row, the second one clobbers the first, and so on and so forth. And the remarkable thing about having this little domain-specific language is that this axiom system, the few dozen that I showed you, is actually both sound and complete. So it's sound, meaning anything we can prove is equivalent using these axioms actually describes equivalent functions. And more remarkably, any 2 equivalent functions we can write in the language using all the features of the language, there is a proof using these axioms that they're the same. And so this gives us a way to do verification in a perhaps simpler system than maybe shipping things off to a solver. Another nice thing about having a language like this is that we can actually exploit some of the mathematical structure that it's built on. And in this case, Netcat has a sort of automata bones. And so we can actually come up with a sort of generalization of the kinds of constructions you probably learned about in undergrad CS, and actually build finite state automata that are completely equivalent to the Netcat programs that we started with. And then we can use that as a slightly more practical way to decide equivalence. So last year we built a tool that does this. These automata are a little more complicated than standard automata because of the states of packets and the way that modifications and tests interact. But you can do this, and then you can decide equivalence by building automata and then comparing the graph structure of those automata using a notion of bisimulation that George talked about. And the performance is actually competitive with tools like Headerspace and others. Here's some simple results that I won't go into, but they're benchmarks, synthetic benchmarks that show the scalability on real-world topologies for properties like connectivity, loop freedom, and also checking equivalence of programs that were generated by a compiler. So this thing actually can be made to scale reasonably well. In addition, you can use this language for verification. You can also use it for programming. So in the spirit of what Shirab was talking about, if we want to start to take some of these building blocks and sort of idiomatically structure them into templates and start to implement various forms of functionality that can be sort of replicated and verified modularly, I think a language like Netcat provides a nice starting point for that kind of thing. And we've started to explore some of these richer constructions. So looking at things like how could we synthesize and generate virtual networks, and that can all be done within the context of Netcat. How can we do things like add a notion of bandwidth and start to reason about traffic engineering? We started to do that, things like fault tolerance and so on. So having this really nice, clean, elegant, lean, automata-based model behind your language means it's very robust. And if you want to try and add new features, you have a sort of set of guidelines that you can use to kind of push that investigation forward. And so having this structure can be very valuable. So in the last couple minutes, I want to talk about some other things you can do when you have this kind of linguistic model. And that is namely connect it to real implementations and also use synthesis to generate some of the low-level tools you would need to run these things in a real network. So if you're in the business of using a language like Netcat, not just for verification, but for programming, you might wonder if the compiler that's mapping from the high-level language down to the implementation could get things wrong. And so one way you can convince yourself that this is not going to be a concern is by actually building the compiler in a proof assistant. This is something that's sort of been a grand vision. Tony Hoare has a famous paper where he basically said building verified compilers is something we should be doing. And it's become quite practical in recent years because the proof assistance and automation has gotten very good. So a couple years ago, we built a verified version of a precursor to Netcat called NetCore, where we actually formalized things like the language, all these forwarding tables, the topology, and we formalized a very low-level machine model called OpenFlow, all in a proof assistant, and then proved theorems showing that our compiler and a runtime system that deals with dynamic changes as the state of the switches is being modified, that all of this correctly implements our nice, clean functional semantics of the program. So when you have a kind of nice, clean language model, you can actually not have to sort of hope and pray when you run these things. You can actually connect them in code and prove very rigorously that the implementations are going to do what you expect. I'm going to skip over this just in the interest of time. OK. Something else you can do when you have this kind of language models, you can start to use it to deal with dynamic networks as well. So one problem that comes up often in networks is that you have to somehow change the program or the policy that you're running. And so you're in the situation where you have the network configured one way, and you want to reconfigure it to some other state. Maybe your security policy has changed. Maybe you want to take some devices down for maintenance. And so you have this problem of how do you get from one configuration to another. And this is hard because in general, you can't take down the network for maintenance, and you also can't sort of update all of the devices instantaneously. So you have to step the network through a series of intermediate configurations that are neither the initial program nor the final program, and somehow this has to behave well. If you do this in undisciplined ways, you can easily end up breaking all the properties that you were so careful to verify. And so we did some work a few years ago where we said, well, maybe we should design update mechanisms where we can get guarantees that although the network will be stepping through these intermediate configurations, they'll still preserve some of the properties of the configurations that we started with. And so we proposed this notion of a consistent update, sometimes also called packet coherence, where every packet or set of packets that's going through the network is going to be processed as if the network was in one of these static configurations. So the network may be going from red to blue to green to purple, but any single packet is going to be processed completely as if it's just in one of those states. Semantically, this is really nice because it means if you've done verification, all those verification properties get lifted from static networks to dynamic networks automatically. And there's also many different ways to implement this. And some folks at MSR, led by Ratul and collaborators and other groups, have developed many different ways of actually providing these kinds of consistency properties. One thing that I'm especially excited about and working on recently is on doing what we call update synthesis. So if you want to have these kinds of guarantees that persist across dynamic changes, one way is to use a very general technique, like some kind of two-phase protocol to implement the update, but that's expensive and wastes a lot of memory. And so if instead you know a specific set of properties that you want to be preserved across the update, then you can actually use ideas from program synthesis to find update programs that get you from the initial program to the final program automatically. And so we recently built a tool where we feed in a property we care about, maybe loop freedom and connectivity, and then we search through the space of possible updates. Here I'm indicating updated nodes in blue, until we find a sequence that gets us from the initial program to the updated program while never violating the property. And there's a bunch of kind of, as George said, you can kind of take things off the shelf from the synthesis literature and start applying those techniques to this problem in networking and get tools that perform quite well. OK, so I'm going to stop there. And I think this is a great session. Thank you to Nikolai and Ratul and George for organizing. I think this is a really exciting time. There's kind of multiple points of inflection that are sort of we're experiencing right now. And I think this idea of having a mathematical basis, a programming basis for building and managing networks is exciting. And I hope some of you will join the party. All right, Victor.
So I have 2 questions.
We can skip the applause in the interest of time.
The first question is, can you do the reverse? Have you tried to take configuration files, parse them out, and create the language, create the program from it?
So yeah, that's the kind of embedding I was talking about, is going from.
So you've done that.
In our case, we take OpenFlow config, so we're not taking Cisco iOS, but we're taking OpenFlow forwarding tables and re-embedding those as Netcat terms.
How hard would it be to take something that is not OpenFlow at this point?
Well, I think lots of people in the room have done that. And also some people at Brown have looked into that. So if you're just talking about getting a static snapshot, then it's pretty straightforward. It's basically a parsing problem. If you're talking about actually handling the dynamics of real routers and their control planes, that's a hard problem.
OK, so that's fine. That was just a simple clarification. So the question I really have is, so are we done now with this? I mean, I'm listening to your talk, and I'm thinking, OK, so he has a language model which can be verified. I mean, things can be verified, and so I'm trying to figure What's
So I think
next?
the place I would say where there's a lot of excitement right now, which conveniently is on my slide, I started from this very simple model of networks as functions and only looking at reachability properties. And those are two huge assumptions that are, there's a huge gulf between that and what people are doing in practice. So one thing that we're looking at right now that I'm excited about is probabilistic semantics. So exactly as in George's knapsack problem, typically you know what kind of traffic will appear at your network. And if you want to reason about congestion properties, even though you don't have perfect knowledge of exactly what packet's going to arrive at the ingress, you'd like to be able to make predictions about how much congestion you're likely to see. And so again, the advantage of having this kind of nice language model is you can start to make the language probabilistic instead of just being deterministic, and there's a nice sort of design recipe for doing that. So that's one area I think is exciting. Another huge area is adding state. I know there's work at MSR and by lots of other groups that's looking at if you want to move away from this model of networks as pure functions, and you want to handle things like middle boxes that have arbitrary, hundreds of thousands of line C programs that are running inside of them, maintaining state, and doing different things to packets based on their internal state. Well, this doesn't handle any of that. I think the sort of methodology should extend, but you're in the kind of hard case of general software verification at that point. And then another interesting area that I know some UIC folks and us are looking at is what about properties that don't just concern a single packet and what happens to it, but possibly multiple packets and how they might coordinate with each other.
Okay, thanks.
All right. So with that excellent talk, thank you very much for attending the session.